Hello and welcome to another video lesson with Lawson. We're going to start looking at acceleration and its relationship to descriptions of motion. You should already be familiar with descriptions in terms of position graphs and describing position or change in position as in displacement, or how velocity is related to changes in position and acceleration. Acceleration is defined as the derivative of velocity with respect to time. If we have the acceleration with respect to time in the form of a graph or a function, then we can take the integral of that acceleration with respect to time and get the velocity. And we can take the integral of that velocity function with respect to time to get the change in position or the displacement. While again, we can see features that look similar to position graphs and velocity graphs, a horizontal line on one of either of those has a different meaning, and as you can imagine, the horizontal line on an acceleration time graph is also going to give us a different meaning. It's going to be a little more similar to the velocity time graph, but not exactly the same. Like the velocity time graph, when it's along the x-axis, that represents no velocity. When the acceleration is along the x-axis, that represents no acceleration. However, that does not mean that the velocity is zero. It means the velocity could be zero or the velocity could be some constant, but that it cannot change. The acceleration being zero doesn't tell us that we're at rest. It tells us that we're either at rest or moving at a constant speed. When an acceleration graph is linear but not a horizontal line, then we know we have a constant change in acceleration. The vocabulary term we use to describe the change in acceleration with respect to time is the jerk of the motion. If we have a linear acceleration graph that's not horizontal, then we know that the jerk is constant. The acceleration is changing at a constant rate. If you see an acceleration graph that has some curviness to it, then we know that the jerk is not constant and that it's actually changing with respect to time. Here we see an example where our acceleration graph is along that x-axis. We know for certain that the acceleration is zero. We don't know whether or not we're moving from the acceleration time graph. Use the integral to get the area under the curve to get the change in velocity. In this case, since our graph is along the x-axis, there is zero area between it, so we expect the change in velocity to be zero. Our change in velocity with respect to time is equal to the integral between our initial time and some time later of our acceleration with respect to time in terms of time. Our acceleration with respect to time is zero. The integral of zero is that constant. So we have some constant c at t minus that constant at t naught. And by definition, since it's a constant, it's not changing, the value minus itself is zero. So now we know that our change in velocity is zero. Without additional information, we don't know whether or not we're at rest or moving at a constant speed, but we do know that we are not changing the magnitude of that velocity. When we look at our displacement, or change in position with respect to time, that will be the integral of our velocity between t naught and sometime later t in terms of t. We know that the change in velocity is zero. We know that the velocity is a constant. Whether it's a constant that is zero or not, we don't know. Since it's a constant, the integral of a constant will be that constant times t minus that constant times t naught, or the constant times the change in time, which matches our previous statements that if we're moving at a constant velocity, then every second that goes by we have a constant change in position. And this matches that. For every 2 seconds, we would have an equal change in position, regardless of whether it was the first 2 seconds or the final 2 seconds. In some cases, that's not true. When velocity is constant, that's always true. When acceleration is zero, that's always true. If our velocity happened to be zero, then this would be the integral of zero, not the integral of a constant. And when you multiply 0 times the initial time, or 0 times the final time, you get back 0. And so again, all we would get out of this is that our change of position is 0 because we're not moving. In this case, we have a constant positive acceleration. It's a horizontal line, so I know the acceleration is not increasing or decreasing, which means the jerk of this motion is 0. However, it's accelerating in the positive direction. Do we know if it's moving in the positive direction? We do not. We don't have enough information to know if it started in the negative direction or started moving in the positive direction. If it was moving in the positive direction, it would be accelerating in the positive direction and going faster. If it was moving in the negative direction, it would be accelerating in the positive direction and slowing down. And if enough time went by, depending on what the magnitude of that initial velocity was, it would slow down until it reached rest, or 0, and then it would be accelerating in the same direction as motion as it turned around and started speeding up in the opposite or positive direction. When we're looking at this graph, again, we can look at the area under the curve pretty easily and see that it's rectangular if we're looking for our change in velocity. Or we can recognize that the integral of the acceleration with respect to time is our velocity. If we're looking at our change in velocity, that's going to be equal to our acceleration with respect to time in terms of time. And now our acceleration is a constant non-zero value, and that means it's going to be that constant 6 times upper boundary minus 6 times that lower boundary, or 6 times the change in time. Which should make sense. If we have a constant acceleration, for every increment of time, we have a constant change in velocity, whether it's between the first and second second or between the second and third second. And as more time goes by, we'll have a larger change in velocity. We can also take the integral to get the change in position. The change in position with respect to time is going to be the integral between our initial time and some time later of velocity as a function of time in terms of time. The velocity at a function of time is 6 times t, which means that this is 6 times t squared divided by 2 minus 6 times t not squared divided by 2, or 3t squared minus 3t not squared. And that is our change in position in terms of that time. Now we can see a constantly changing acceleration. Once again, we have a linear acceleration graph, but it's no longer a horizontal line. It's a line at an angle. Constant positive slope, which means we have a constant positive jerk. However, our initial acceleration was negative. So we had a negative acceleration, or we're accelerating in the negative direction, and over time that decreases until we have 0 acceleration, and then it increases in the positive direction, where we have a greater and greater magnitude of acceleration in the positive direction. While again, we could look at the change in velocity pictorially by imagining the area under the curve and talk about the point at which our change in velocity for the initial couple of seconds where it was negative is equal to our change in velocity for those couple of seconds after 2 seconds where it is positive, and they cancel each other out, where our net change in velocity has actually been 0. We can also look at the function which describes this graph, which is 6t minus 12, and be able to find the velocity. So we can find the change in velocity by looking at the integrand, or the integral of that function. Change in velocity is going to be the integral of our acceleration with respect to time in terms of time from our initial time to some time later. This is a constant times the variable t, which means it is 6 times t squared divided by 2 when we integrate it, minus 12, that's a constant, and that's going to be minus 12t for our upper boundary, and our low boundary is going to be 6t naught squared divided by 2 minus 12t naught. When we clean things up, 6 divided by 2 is 3. we distribute the negative, we should get 3t squared minus 12t minus 3t naught squared plus 12t naught. This gives us our change in velocity over that time interval, or the area under the curve for that function. If we want to get change of position, that's the integral of the velocity function. That's going to be the integral of velocity with respect to time in terms of time from our initial time to some time later, 0. We can see that these difference gives us our change of velocity, which means our velocity function with respect to time would be 3t squared minus 12t, technically plus c, some constant, and that means that the integral of 3t squared is going to be 3t cubed divided by 3 minus 12t squared divided by 2. That would be plus some constant c. Subtract from this the lower boundary of 3t naught over 3 minus 12t naught squared over 2. We can see this cleans up a little bit, and your change in position, 3 divided by 3 is t cubed minus 12 divided by 2 is 6t squared. Distributing the negative, minus 3 divided by 3 is 1, minus t naught, and plus 12 divided by 2, or 6t naught squared. And now, based on the time interval, we can find the change in position, or the displacement, during that time. And finally, we have a non-constant jerk. We can see here, not only is the acceleration changing, it's increasing and then decreasing along a sinusoidal pattern. We start at 0, reach a maximum positive, return to 0, reach a maximum negative, return to 0, and repeat the process. Since we have the acceleration as a function of time, what we're going to do to be able to figure out the change in velocity is integrate. So our change in velocity with respect to time is going to be the integral between our initial time and some time 0 of our acceleration in terms of t. The integral of sine is going to be negative cosine, and then we notice we have this pesky constant in here, half of pi, or pi divided by 2, or 0.5 pi, however you want to say it. So the integral of this, the negative of cosine of the internal, I'm going to write it as pi divided by 2, but the same as 0.5 pi, times t, all divided by pi divided by 2, which is the same thing as multiplying it by 2 over pi. Then we have to subtract from that, or the lower boundary, which is going to be the negative cosine of pi over 2 times our initial time, or t naught, times 2 over pi. This negative of a negative ends up being positive, so we can kind of flip this around, interestingly enough. This becomes cosine of pi over 2 times t naught, all times 2 divided by pi, minus 2 times cosine of pi over 2 times t over pi. The displacement over the same time interval. So we're going to look at the change in position. We're going to integrate between our initial time and our final time the velocity as a function of time with respect to time. And when we're integrating a constant, we end up multiplying it still by the same constant. And then because it's cosine of pi over 2 times t, we'll end up taking the integral of cosine, which is sine, and then again dividing it by pi over 2, which 2 times 2 will end up being 4 times the sine of pi over 2 times t over pi squared minus 4 times the sine of pi over 2 times t naught over pi squared. Hopefully you're starting to get a better grasp of what some of these variables represent and how we can see graphs of these different variables to represent their motion, or based on their graph and a function that might describe their graph, determine values that would match some of the variables or allow us to model and make predictions about the motion, including what the change of position is, what the change in velocity is, what the acceleration is. And with some additional information, we can also find position, the final position, or the initial velocity and the final velocity.